4.6 is an introduction to titrations. We actually have done titrations before. We did this in Chemistry 1. It's called volumetric analysis, and it's a technique that's used to determine the amount of a certain substance by doing a titration. So I have a picture on here of a burette and a solution that when you add the base, it turns pink, and the pink indicator is phenolphthalein. Remember, we did it in Chemistry 1. We wanted to get the lightest pink possible, and we did it, we had a competition for Molex. No, we are not going to be doing that in this class, since you've already done it before. But we will do some labs with titrations. We can even do a titration without a burette, but just by adding drops with a pipette instead. But a titration involves delivery, usually from a burette, of a measured volume of a solution of known concentration, called the titrant, into a solution containing the substance being analyzed, called the analyte. So usually the titrant is what is put into the burette, or you know everything, like you know the concentration of that. And then maybe for the analyte, you don't know the concentration, so you're going to want to figure out what that concentration is by doing some math. So the point in the titration where enough titrant has been added to react exactly with the analyte is called the equivalence point or stoichiometric point. This is often marked by an indicator. Actually, we're going to get into this with acids and bases and later on, but the indicators usually turn right after the equivalence point at the end point. And so it's just slightly off, but we assume since they're pretty close to each other that when it changes color, you're done. You've reached the equivalence point. So we'll deal with that more when we get into acids and bases later this year. But again, the point where the indicator actually changes is called the end point of the titration. Now, the whole point of the equivalence point is that the moles of your titrant, are equal to the moles of your analyte. So that means that when you have the moles equal the moles, then when you solve for the moles of the titrant, so how much did you use, then you know that that is exactly how many moles are in your sample of the analyte. And then you can use that to take it further to find concentration or whatever you're else trying to find about the solution. Okay, so we have example 8, and that's all for 4.6, just to review how this problem could go. A student carries out an experiment to standardize, which means to determine the exact concentration of, a sodium hydroxide solution. To do this, the student weighs out 1.3009 grams of potassium hydrogen phthalate, which is abbreviated as KHP, but it's not potassium, hydrogen, and phosphorus, FYI. We just abbreviate it as KHP. The molar mass of the KHP is 204.22 grams per mole. The student creates the solution, uses an indicator, and titrates the sodium hydroxide to the endpoint. The difference between the final and initial burette readings indicates that 41.20 milliliters of sodium hydroxide solution is required to react exactly with the 1.3009 grams of KHP. Calculate the concentration of the NaOH solution. Okay, well, we want to know the NaOH concentration. So we want to know the molarity of the NaOH. Okay, what we do know about the NaOH, the sodium hydroxide, is that we used 41.20 milliliters. Okay, we know that we used 1.3009 grams of KHP, and we know the molar mass of the KHP. So what we're going to do is we are going to use the KHP to solve for moles. And remember, the moles are equal to the moles. The moles of the titrant, T for titrant, are equal to the moles of the analyte, A for analyte. Okay? So when you know moles of one, then you know moles of the other. And that will help us to find the molarity of the sodium hydroxide. So we need to take our mass of the KHP and turn it into moles. So we'll divide by the molar mass given, which is 204.22. And like I said, moles are equal moles, so I'm just going to do a little switcheroo where I'm going to say 1 mole of sodium hydroxide is equal to 1 mole of KHP. Now if it wasn't exactly 1 for 1, we'll get into this with acids and bases later, but when it's not exactly 1-for-1, you will be told, like maybe there are 2 acidic protons or something like that. But for now, you can just know that it's a 1-for-1 deal. Okay? So solving this out for moles of sodium hydroxide, I put mine in scientific notation. I have 6.37 times 10 to the negative third moles. Now, I know there's more digits, I just didn't write them all down, but I left them in my calculator when I solved for next step. Okay, this is not the end yet, because we want concentration. We want molarity. Molarity is moles divided by liters. So we would just take this amount divided by our volume changed to liters, so 0.04120 liters. So the concentration in molarity is 0.1546 molar sodium hydroxide. Okay, so our next lab will probably deal with this, but just it's another way to use stoichiometry. It's another way to use mole ratios, that kind of thing. The moles equal the moles. That's the most important part to get from titrations.